Hi everyone, this is example 1 from module 2D on page 58. So remember to read through your vocabulary on page 57 before starting to work through these examples. Example 1, we're looking at a density curve, and this is a histogram of Iowa test vocabulary scores of all 7th grade students in Gary, Indiana. So the Iowa test is taken in other states besides just Iowa. In this distribution of the histogram, there are 947 students total. So part A wants us to describe the shape, spread, and center of the density curve. The line is drawn above the curve to show us what symmetric would look like. So I would say this curve is close to symmetric. The center looks to be around a score of 7, between 6 and 8. And then the spread ranges from 2 to 12. Question B tells us that 100% of the 7th grade students are included in the histogram. So remember, there are 947 students total. 287 students had vocabulary scores of 6.0 or lower. So what percent of students had vocabulary scores that were 6 or lower? And then you can come up and find 6, and you guys can shade the bars that are over on this side. So to find the percent, we're going to say 287 out of 947, and we'll use division to figure out that that is 0.303, which is 30.3% of students. So 30.3% of students scored 6 or lower. Now it's asking us to calculate what percent of students had vocabulary scores higher than 6. So we could go through subtraction and figure out how many students different that was and then calculate. An easier way to do it is that we know that this graph contains 100% of the 7th grade students. So we can use that fact to calculate 100%. Subtract 30.3% of the lower scores would total, this must be 69.7% of students scored higher than 6. And you can double check my calculations with your own calculator and make sure I got everything correct here. Now it tells us 635 students had vocabulary scores of 8 or lower. What percent of students had vocabulary scores higher than 8? Aha! So this is another example of calculating the opposite, or what we call the complement. So we know there were 947 students. So I'm going to say 947 subtract 635. And from my calculator, I see that's 312 students scored higher than 8. Now to figure out the percent, I can say 312 divided by the 947 total students, and I get 0.329 if I go to 3 decimal places. And as a percent, that's 32.9% of students scored higher than 8. And there are other ways you could do this. You could have figured out the percent who scored lower than 8 and then used our same method that we used in part C of subtracting from 100%. Whichever way you went, you should have ended up at our same answer. Okay, let's go look at now example 2 on page 59. So this is what's called a skewed curve. If you look at it, you see that it's got a tail out to the right side. And the graph shows survival time of guinea pigs from a scientific study in hundreds of days. So guinea pigs usually only live around 1 year. So a guinea pig that lives longer can maybe live up to 2 years, but few guinea pigs do that. So using the histogram bars, and it tells us the frequency numbers up here, count the total number of guinea pigs in the study. So we want to tally up all of our frequency values here in the table. You can see over on the graph is missing the y-axis. So if we tally up everything from the table, we're going to calculate 32 plus 30 plus 4 plus 2 plus 1 plus 3. And I'm going to tally this up on my calculator. You guys can follow along. So I got 72, so check to make sure that I calculated correctly. So this is 72 guinea pigs total. So now it wants to know what percent of guinea pigs survive 200 days or less. So 200 days or less would be 30 plus 32, or 64. Now we have to calculate what percent is this. So we can say 64 out of 72 total equals, from our calculator, we get 0.888 or 0.889 if we round it, because the 8s keep going. So 88.9% of guinea pigs survived 200 days or less. And so now they're asking what percent of guinea pigs survived more than 200 days. So we have a couple options here. We could calculate out the difference. So let's do it the first way. We could say 72 subtract 64 equals 8 guinea pigs. And remember, 72 is the total and 64 lived less. And then we could do 8 divided by 72 total. And if we do that, you get 0.111, or if you make that a percent, you get 11.1% of guinea pigs survived more than 200 days. Now, if we want to check the other way, we could say, well, we know they have to total 100%. So if we check 100% subtract 88.9% from up above of the guinea pigs that survived 200 days or less, we see this difference is also 11.1%. So either method gives the same final answer. So in part D, we can say either method gives the same answer. And then they're asking us to, how does this compare to the area under the density curve? So if we look back around 200 days, does this look like 11%? And this smooth density curve, it looks like most of the area is below 200 days. So we could say in the smooth density curve, it looks like most of the area, or about, we could say 90%, is below 200 days. So in my opinion, the smooth density curve does seem like a pretty good fit. Let's go ahead and look at example 3 on page 60. This is what's called a uniform density curve. And see how it's just 3 bars side by side? It's not, no peaks, no tails. It's just every mile here has the same height. So this example is on a level 3-mile bike path. Accidents occur uniformly along the length of the path. The graph here describes the distribution of the accidents, and it's a rectangle. So we have to ask ourselves in part A, does this uniform graph satisfy the requirements for a density curve? So if you look back at our vocabulary, a density curve is a curve that has only positive y values and contains 100% of the population data. So this graph has only positive y values. It only goes up to 1/3. And the other requirement is that it contains 100% of the population. So this graph, we've got 1/3 plus 1/3 plus 1/3. Well, 3/3 is 100% of the accidents. So we can say this graph has only positive y values, no higher than 1/3, and contains 100% of the accidents. And then we can calculate, well, 1/3 plus 1/3 plus another 1/3 equals 3/3, which is 1 whole, which is 100%. Question B asks about the proportion of accidents that occur in the first mile of the path. And it says this is the area under the density curve between 0 and 1 miles. So what is this area? Well, we can see it's 1/3. And the reason we can see this as 1/3 is if we think about the area of a rectangle, we can think, well, length times width. In this case is going to equal 1 times 1/3. So that's how we're coming up with that calculation of 1/3 of the accidents. And then it tells us Chandra's Yard adjoins the bike path between the 0.8 mile mark and the 1.1 mile mark. So we want to figure out what proportion of accidents happen next to Chandra's Yard. So we first need to calculate out what is the length of Chandra's Yard. So that's going to be the 1.1 mile minus the 0.8 mile. So Chandra's Yard is 0.3 miles long. So she has a pretty long yard there. And then the proportion that happened next to Chandra's Yard is going to be the area calculation. So we know that the length of Chandra's Yard is 0.3 miles times 1/3 of the accidents happen every mile. So if we do 0.3 times 1/3, we get right around 0.0999999, and then the 9s keep going. So we can round this to 0.1, which as a percent would be 10%. So we can say about 10% of the accidents happen next to Chandra's Yard. Oh, so we just answered the percent question in part D. So I'm going to copy and paste this for part D. And a proportion is when we write it as a decimal. You should remember that from vocabulary page, I think. So the proportion is the 0.1, and then down here in part D, when it's asking about the percent, that's the 10%. So remember, when we ask about a proportion, that's a decimal answer, and when we ask about a percent, that's when you go ahead and convert it to a percent answer.